So let me introduce our next presenter. And again, I should apologize. Our schedule is a little bit behind, but not too bad. Bryan St. Clair is an independent experimentalist and the founder of St. Clair Tech R&D, which is focused on a variety of alternative technologies, including new work building upon the inertial propulsion framework developed by Branson Roy Thornton in the 70s through the 80s. So, Bryan, it looks like you're already here.
Yeah, I'm here. Thank you very much. Can everybody hear me okay?
Absolutely. Bryan, take it away, sir. And thank you again for joining us.
Matthew, that was awesome. That is a really tough act to follow. Okay. Anyway, thanks everybody. Thank you, Mark, and all of you for inviting me here to this. I just wanted to talk about what we're doing with inertial technology. There have been a few developments. There have been a few changes in the way we've thought about it. A couple of things that we're not going to do is we're not really going to go down through the heavy math on this. That's something that would just bog down the presentation dramatically. I do have a couple of videos that I'm going to be presenting. If the background noise in the videos is too loud, I apologize. So, you might want to pay attention to that as they come up. I wanted to also say, I know a lot of inertial propulsion, much like the anti-gravity and UFO, UAP field. It's been ridiculed. It's been silenced. It's well over 100 years of just sweeping it under the rug. The established scientific community obviously says it's not possible, but there are a lot of things that we know are possible that somebody somewhere just doesn't want to admit because it doesn't fit into their mathematical model. So I know that before I begin, I also want to say, this is not a miracle technology. This is not meant to rise up off the ground and send us to the moon immediately. I kind of see this as the Model T of inertial propulsion at this point. My point is that it does work. It absolutely does work. It's been proven over and over and over again with stiction and without stiction, with a lot of different types of media to move it in and through and across. So anyway, I'm gonna try and share my screen here. Let's see how this works. And we're gonna go full screen on this if we can. There we go. All right, so I appreciate everybody having me here. Like I said, I'm going to talk today a little bit about our pulsed inertial technology, engine technology. We're called knowing it as PIETECH, which is very simply for pulsed inertial engine technology. There we go. That's basically the setup of a single disc which would be in operation. It is very similar in appearance to what we saw with Roy Thornton's inertial engine that was known as the EZKL, or Ezekiel, which stood for Energy Zone Kinetic Lifter. Roy's story is available in print from Tom Vallone. I saw him on here earlier. The Integrity Research Institute, he's got much of that available for anybody that's interested. First off, who am I? Nobody's really heard of me. Well, that's fine. I've been a full-time professional automotive technician for over 35 years. I'm a trained machinist. I hold a lot of certifications in both trades, automotive machining, technical machining, manufacturing machining. I have several degrees in auto repair, a main degree in auto repair, and a bachelor's degree in transportation. I'm also dual ASE certified, so I kind of do know what I'm talking about when I'm talking about cars and transportation and propulsion systems at least as far as transportation on the ground. I also have management training, and I've managed several garages, different sizes, fleet shops, trucks, cars, and everything in between. Years ago, I did a lot of dabbling in alternative fuels, alternative energy, and that's led up to the alternative propulsion systems. That's been going on ever since I was a teenager. Back in the 1980s, I built a cold vapor carburetor that worked really, really well. It unfortunately was at the time that carburetors were going away, fuel injection systems and computers were coming on. So that kind of fell off the edge. I was also trained in industrial model making. A head of a multinational industrial model shop was the one that trained me on how to do this. We worked directly with the engineering departments, and the engineers would come down, bring us prints, and we'd say, hey, we can't do this. Can you make this a little different? We'd switch it back and forth. We did a lot back and forth that way. Now I'm running a small shop that affords me a little bit of extra time to do this kind of thing. So let's see. What is PIETECH? Pulsed Inertial Engine Technology is simply a propulsion system. It does not push on any physical media or eject any mass for propulsion via reaction. So that's what we used to call reactionless propulsion. We don't call it that anymore. There is no such thing as reactionless propulsion. Everything has an action and reaction, whether it's internal or external. The PIETECH system can be used either in a full atmosphere, a zero atmosphere, in full gravity, zero gravity. We've done some tests during free fall. We've done some tests with wind tunneling in both directions, side wind tunneling, and it works. It just simply works. It can be used as a primary propulsion system. As it gets stronger and as it gets better, of course, it's going to be a little bit more efficient in that area. Right now, we're looking at it more as a supplemental propulsion system. Think hybrid cars. This would be a system that could be added into any type of vehicle, especially if it's transporting people, whether it's on the ground or in the air. It really wouldn't matter. Think about a hybrid airplane. There really is no such thing, but this could conceivably cause that to be a normal everyday operation. So what is PIETECH? What it's not pseudoscience. It's not anti-gravity. It's not a warp drive. It's not a lifting system. It's not attempting to break any laws of physics. And mainly, it's not difficult to replicate. Anybody can really build one if you've got a halfway decent shop and some mediocre even technical skills. I'm not here to prove anything. I'm not here to disprove anything, and I'm not here to argue the point one way or the other. I've got a lot of emails wanting to argue the point. The tremendous amounts of emails. People wanting to argue the point. This isn't possible. I know I've spoken with Mike Gamble, and he said the same thing, that he'll gladly answer anybody's emails as long as you don't start out with, you're breaking the laws of physics. This isn't possible. So I fully understand where he's coming from with that. This presentation will not include, these are very important points of what we're not going to talk about. Untested theory. If it's not been tested, I'm not going to talk about it. Everything that we're going to discuss has been tested. It's been proven. So we're not here to prove anything. We're not here to discuss untested theories. I'm not going to go down through the mathematical formula. It's pretty simple. The problem with the mathematical formulas that we've got right now is that it's not that they're incorrect. They're not. They're incomplete. They're put together incorrectly for what we're doing with this. So that's why mathematically this shouldn't work. But it's not the fact that mathematically it shouldn't work. It's mathematically it's not been shown why it can work. I'm not going to do an academic tutorial on how to build one. We're not going to build one this evening. This afternoon. We're simply going to talk about what it is, how it works, the different stages of what it does. And unfortunately, I'm not good at computer graphics, so we're not going to have fancy graphics in this. I'm here simply to present a mechanical system with working prototypes, and we're going to present the working prototypes that are currently being tested. What is PIETECH capable of propelling? Virtually anything that moves. Like I said, can you imagine having an electric hybrid, otherwise fossil fueled airplane, whether it would be a prop plane or a jet plane or a space plane? It's absolutely incredible in the fact that we can supplement the propulsion system on virtually anything at this point. It doesn't matter whether it's on the earth, in the air, in space, in the water, under the water. It really doesn't matter. It simply works. How is this different? There have been a lot of different ones out there, and I don't want to bash on anybody's systems, because everybody's put out a tremendous amount of work on these things, and I really want to show a lot of respect to those people. Branson Roy Thornton was the one that came up with the entire stationary sun gear system that we're using right now. But this does different from his system, from some of the others, in ways that we just didn't expect were going to happen. We have combined multiple technical methods into a single system, and it doesn't not rely solely upon one component in that technology. It can be easily used in conjunction with virtually any other vehicle propulsion system. It does not matter what the propulsion system currently is, it will work with it. And it can be fully self-contained. The battery, the charger, the power plant, everything in a sealed container with a simple on-off switch, or it can be directly connected to a vehicle so that it would have onboard control systems. I wanted to do a quick timeline of the vehicle, the PIETECH project's development up to this point. It's a very quick video. I apologize if the background audio is a little much. I tried to drop that down and maybe add a little bit of a musical background, but that was probably not the best idea either. So without any further ado, that was the very first set of gears that we tried. That was the very first Thornton prototype that we put together that actually did work. It would actually self-propel. That one had enough power to not only propel itself, but it would actually push objects up and down the workbench. On to the next model. This is where we started calling it a PI, not just a Thornton Ezekiel drive. One of our projects has been actually worked on overseas. Tokyo Muramatsu, he's really helped a lot. And I thought this was an incredible little piece of video. This was the first time I ever saw anybody ride on any kind of an inertial propulsion system. It was just absolutely amazing to me. And this is where he is actually developing it a little bit further and a little bit further. That is his ongoing project at this point. This was the first time that any of them had been really videoed mounted in a motor vehicle. We were getting ready to do our first road test. That's that same unit before it was mounted in the vehicle. And on to the system that we're putting together now, which is the 4 series PI systems. We've made some considerable improvements since the originals. This was the first time that we actually had the new propulsion system actually moving with its new outer stops. A lot of what we're using right now, in the latest one is all in this model. And coming soon, we're going to have the PIETECH, X not standing for the 10, but standing more for an internal design of the unit. It's kind of unknown at this point. So X kind of works for both of those. All right. The combined technologies that we are using: gyroscopic precession, gyroscopic time-based shifting, centripetal inertia, mass acceleration and deceleration, impact thrust, and it's all controlled both with mechanical and electronic controls. Those are the things that really make this a lot different than some of the other systems that have been out there. We'll cover what those items are and how they're in play in the system. The gyroscope and the gyroscopic precession, they're only slightly in play for the actual propulsion of the system. There are effectively multiple gyroscopes running in each unit, and it really works more for stabilization of the rotating assemblies than it does for the propulsion itself, although it does play into the propulsion itself. A 4D gyroscope, gyroscopes with a time base or velocity shift, those have been what are shown to have some serious different effects, not just the standard gyroscopic effect with being able to stabilize and things like that. The alternative gyroscopic phenomena tend to present themselves when the time shifts and the velocity changes are introduced. And without them, even with the other technologies, the time shift is part of the system that makes it work as well as it does. The centripetal force, of course, you know, we utilize the centripetal force. That's much like the Ezekiel was, Roy's system, changing the arc radius of the weight orbiting the center axle. It comes in closer, it goes out further away. And that's simple, plain, everyday centripetal force. That alone is not going to be enough power to make a system that could move a motor vehicle. The mass velocity changes, those also were happening in Roy's system, and we've really expanded on that quite a ways. The reciprocating mass accelerates and decelerates during each cycle, not only when it comes to the center and touches off in the center, but also when it gets to the outside. It also slows down as it approaches center and speeds up as it leaves center. So we've got some serious velocity change going on there. The acceleration and deceleration of the mass is because of the position in the cycle. The mass caused acceleration, deceleration of the mass caused by the rotational speed change, which is the speed differential control. That's the electronic control that we've added to it that boosts the speed just about the same time that you would normally see it slowing down because of motor load. And then we have the sudden deceleration of the mass due to contact with the stops. Years ago, Roy called those stops a whole different set of things. He never even used the word stops in his system. We use stops. They're not brakes. They're not traps or anything else that he used in some of his dialogue. The impact thrust, that's got an awful lot to do with it. And I know Tom Valone spoke about the impact thrust having a lot to do with Roy Thornson's system. That is the thrust that's caused by the moving mass impacting another portion of the assembly. The mass impacts with the center axle, pushing everything forward. It impacts again with the planet gear mounted stop, with the outer stop, which we've improved dramatically as well. The impacts equal sudden mass deceleration, and we have changed those weights to not simply be a weight as such. It's not just a hunk of metal or a hunk of something going around. It is actually a dead blow weight, much like a dead blow hammer would be. It's hollow, it's filled with shot, and that effectively lengthens the amount of time that each impact has effect on its stop. The mechanical and the electronic controls, they're pretty straightforward. The mechanical control uses the planetary gears to continuously modify the movement and the inertia and the mass velocity. The mechanical stops, therefore impact and mass deceleration. The electronic control of the drive motor, base speed. We have a very simple speed control system with the speed differential controller on it, which is the electronic control of rotational acceleration and deceleration. So the whole unit speeds up and slows down, depending on the design of the unit, 2 to 4 times per revolution. Step-by-step function of it. This was a picture that was generated by my friend Tokyo, and this shows basically starting out. Okay, we've got one weight out front. This is the progression as the unit is trying to move forward. It's moving from right to left. It's a little bit hard to follow because it's not in motion in the picture. So I wanted to show this quick little orbital cycle. This was also generated by Tokyo. This shows the actual cycle of a single gear and weight assembly. Impacts center, comes around, impacts the outer stop. And again, this is in motion from right to left, and depending on the speed of the rotation would depend on the timing of when it would impact the center and impact the outer stop. The outer stop is fully adjustable, so we can actually change that correlation between the time when it hits the inner and the time that it hits the outer. We'll go through real quick. When in position 1 in the center, when the weight is in the center, it's contacting the center axle and it comes very near to a stop. This is right here is where it would impact the center on the left, the center position with the weight not in rotation anymore. Momentarily, it hits that and it simply stops in its rotation. This particular series is moving from left to right, and you can see that it would be hitting the center and pushing the assembly to the right. And then as it leaves that center position, this is where the power stroke really begins. What I call the power stroke, that's where the power of the electric motor that runs this is really under its heaviest load. That's also the place where our speed differential control starts speeding everything up. Position 2, that power stroke, as I was just saying, the movement is sideways to the direction of travel. Therefore, it has little or no effect. Now, that means that when it's swinging out here, it's trying to push sideways. It's not moving forward or back. That's why 2 wheels in counter rotation work so well with this, because it counters that. It has little or no effect on the actual propulsion of it. It does add to vibration of it if we don't use a counter rotating unit. That is exactly where the speed differential control would accelerate the RPMs. As it comes up and hits the outer stop, this is the older design outer stop. We had a simple metal block welded to the gear and another metal tab welded to the backside of the swinging weight assembly. It would come up against this and it would literally just simply jerk the whole gear in the direction that you want the unit to move. This generally just converts that unit into that unidirectional thrust. This is also where the gears are under their most reverse thrust and where we've broken a lot of gears. That's why we're using gears that we can throw together, we can tear them apart, and if we blow them up, we throw them away and we don't worry about the cost. when we started out looking at machine shop gears, the cost was going to be very prohibitive as soon as we started realizing we're going to start blowing gears and tearing teeth off of gears on these things. Position 4, when the thrust begins, it continues until the weight reaches a point at or near just past its apex, the apex being considered when the weight is furthest away from the center axle. At this point, that's where the speed differential control has released. It's returned the RPM of the whole rotating assembly back to its normal RPM setting. In position 5, we're coming back around. We're basically done propelling. You could really look at this as reset. It's resetting to do the job over again. So during this period of time, if we had another set of gears and wheels in operation, this was when they would help take up some of that pulse so that it wouldn't pulse as badly, and performance, of course, would be greatly improved. The dead blow weight, I'm telling you, that really made a significant improvement. That was a game changer with this whole thing, because when it hits, that dead blow weight just really helps out the propulsion. And at that point, the rotating cycle begins all over again. Adjustments are really critical on this. When I say they're really critical, gross overall adjustment is very critical. Minor adjustment is, but it's not. We can tweak it and peak it and get a little bit more power out of it with the minor adjustments. But the first important point of adjustment, excuse me, the outer mechanical stops. At the point when we're generally using 2 weights on a single wheel on our units at this point. And at the same point when the rear one is contacting the center, that's just about the time when the front one is about to or has just started to contact the outer stop. That actually doubles up on both of those impacts. So we're getting 2 impacts for the price of 1. It really has been, like I say, another game changer. The second important point of adjustment is where exactly where in the rotation everything comes to that impact. Generally, it's going to be with the forward weight in the 20 to 45 degrees before it gets to apex. That has worked out really the best for us. I know Roy talked about that in some of the things that he wrote. He was of the impression that 30 degrees was just about right. I've found that it really does depend on how heavy the weights are, what type of weights you're using, and how fast you're rotating the entire unit. It is speed dependent. It does work at very low RPMs. It also works well at reasonably higher RPMs. What it does not do is it does not work well at very high RPMs. So this adjustment is made by adjusting the position of the sun gear. Basically, we unlock the sun gear and rotate it, and that simply repositions where the weights are going to be hitting their stops. And like I said, this is an adjustment that's not so much made by how many degrees before dead center, before apex. This is an adjustment that is made by performance. And performance, at this point, we're measuring a lot of our performance using a force meter, an electronic force meter, so that we can see forward propulsion, rearward propulsion, and we can even hook it up sideways and see how much sideways propulsion we're trying to get rid of. That vibration. So one thing that is important to note, that once this is really and truly incorporated into a vehicle design, it could be reversed. Simply by putting an actuator on that center gear, we could turn that center gear around completely backward, and you would actually have an inertial system that would not just propel it forward, but it would actually pull it backward as well. nice for a braking system, nice for a positioning system, terrific for sideways movement because it can be repositioned in any direction that you would want, 360 degrees around. The third point of adjustment, the speed differential control, that's what we were talking about, speeds it up as it gets into its power stroke, so to speak. That's adjusted to increase the rotation speed when the rear masses are just about ready to leave the center axle stop. This is easily identified using an ammeter, especially if it's hooked to a lab scope. We can identify the exact position where that speed differential control should trip in by the exact moment that the motor amperage starts to rise. The speed increase, it cuts off just before the mass reaches its apex position. That is nowhere near as important as when it begins. It's nice to have it maintain the higher RPM until it gets just about to the apex. But if it stopped a little sooner or a little bit later, it really wouldn't make as big of a difference as it does when it starts increasing the speed. The fourth point of adjustment, the RPM adjustment itself, the speed differential control should be a 75 to 100% increase above the base RPM. So if we're running the base RPM at 100 RPMs, it should raise that RPM level to 175 to 200 RPMs just for that moment of increase. The optimal RPM settings are yet to really truly be determined, and they're currently being adjusted by monitoring performance. And a lot of that, the bigger and heavier it is, the slower it likes to run. The smaller and lighter it is, the faster it likes to run, but only up to a point, and then it becomes self-destructive. The fifth important point of adjustment are the phase adjustments, and that's something that a lot of people have not really looked at very much. The two masses on a single wheel can reach the apex at the same point in rotation. The variance between those 2 points should be less than 20 degrees. That means that within that 20 degrees, you could have the center, the weight hitting the center pin, maybe 20 degrees sooner, maybe 20 degrees later than the outer one does. That will actually increase the amount of time of propulsion. So it can be a good thing. It can also be a detriment because if it's increased too much, then the pulse is not high enough to really be strong enough. So it's something that has to be weighed out between the two, and that's all been done at this point just by monitoring the performance. The goal of the PIE is so far determined the phasing of the wheels. The wheel phasing as a propulsion assistance device can be 90 degrees out of phase between the two wheels. So if you've got a right wheel and a left wheel, or a top wheel and a bottom wheel, they can be 90 degrees out of phase with one another. It does create a little extra side to side vibration to do that, but it also helps as a hybrid type, a helper pusher design. If it's made for self-propulsion without anything else helping it move, then pulsed all at the same time, synchronized very closely, is really the better way to go, as it simply works much, much better. The important noted observations, 7 of the most important ones that I wanted to speak about real quick here. Phasing can be changed, obviously, depending on usage. As we just spoke about, the phase, whether they're phased together or they're phased 90 degrees apart, 45 degrees apart. The more wheels and that you would use, and the phasing could be changed for smoother operations. Multiple components, they all have to work together. If they're not adjusted properly to work together, it's just going to tear itself apart, and we're not going to get any propulsion out of it. Longer impact times from the dead blow weights have been a real game changer. That's something that as far as I know, nobody else has tried in any of their systems. It works exceptionally well. The speed or RPM changes are of primary importance. We've seen that in Tolkien ship-off devices and other similar units that have shown some degree of operation. And it's shown to be a real big part of the efficiency of this design as well. The stops, all the stops have to transmit impact very firmly. They can have padding on them to reduce noise, but too much padding and the impact is also diminished, and therefore so is our propulsion. Something that I'm going to come back to this in a couple of minutes, inertial Doppler. This is something that is something that I've never heard anybody speak about before. I've not seen anything written about it before. I know a little while ago, my ears perked up when Michael Boyd said quantized inertia. And that may be a lot of exactly what we're talking about, that it is a measurable phenomenon. We're calling it inertial Doppler. It may not be an accurate description, but for now, that's what we're using. And the last, and I think that one of the very most important things that we need to do is we have to have collaboration with other experimenters. We need independent experimenters to be building units and verifying operational points, and we can all work together to make these things work just so much better. So the terminology of inertial Doppler, it might not be technically accurate. The fact remains that the faster a vehicle is traveling with a pi unit in it, the stronger the pi becomes. So is that because of this is a good question for the group, for anybody out there that may have some idea about this. Is that caused by an inertial Doppler effect? Are we actually making a Doppler effect of pushing energy out in front of this? Or are we simply pushing harder against its own mass and causing a stronger pulsation? Either way, I'm not 100% sure which is true. We've got a lot of testing to do before we would absolutely know one way or the other on that. If I was to indulge in a little conjecture, if any energy manipulation is involved with using and recycling inertia, those energy fields could exhibit a Doppler-like effect, and that's just like what Michael was speaking of with quantized inertia earlier. More study and testing is going to be necessary. We're going to need to understand this a little better. I think we need to understand this a lot better. The effect is experienced in a moving vehicle. It's measurable, it's undeniable, it's there, it's real, it's true. The design changes from the early days to where we are at now. We had counter rotating and same rotating units. We've had them that were driven by a timing belt that were side to side. We've used the double decker design with a roller chain drive. The roller chain drive was another good change that we added because there can't be any slippage, and timing is always held much better with a chain. The belts with their soft teeth sometimes tend to slip a little, or they'll just even have a little bit of a deflection, and that's caused some problems. We've added ramps on the ends of the weights. They've actually they serve two purposes. They hold the weights in center a little longer. They also keep those weights from jamming against the ends of the end of the weight jamming against the center pin. If you go back and look at some of the videos of Roy Thornton with his demonstrator units, he had that same problem. This has completely eliminated that problem. We have zero jamming anymore. The gear motor with the speed controller, that was a huge improvement. It's strong, it's smooth, it draws very little power, and it's very reliable. The dead blow weight design, as we spoke about before, that increases the amount of time that each impact happens. And that was a real game changer for the overall design. The speed differential control, adding that fourth dimension to the gyroscope, fourth dimension being time, height, width, depth, and then time, has been a real big deal. And then, of course, the very last major change that we made was the improved adjustable outer stop system. And that has really been a big improvement on how energy is transmitted during that outer stop sequence. Just a few pictures of the different ones. We've got the counter rotating, and then we've got same rotation. We've got the double decker, and that leads us up to where we're at right now with the Pi 4.8. And in the picture, I hopefully you can see my cursor. We've got the gear motor. We've got the new improved outer stop design. This way, when the weight comes around and hits the end of that bolt, that's adjustable so that we can change the timing between when it's contacting the center and when it contacts that outer stop. Those are all big improvements in the way it works. And right here you can see the actuator for the speed differential control. There's actually a micro switch. We're not using sensors. This is plain simple electrical, no electronics other than the speed controller. Plain micro switch on a ramp type actuator. Things that didn't work, I like to talk about the things that don't work, because if I only talked about the things that do work, number one, I'd be an idiot. That's all there is to it. You know, we all have things that we try that don't work. And if we ignore those, we don't learn and we don't move forward. So the things that didn't work well or didn't work at all, the very high speeds, they're very destructive. At this point, I've not had one that runs at a high speed that will actually hold itself together long enough to self-propel. 3 weights per wheel, it sounded like a great idea at the time. Let's make a triangular pattern and have 3 weights, 3 gears rotating on each wheel. Did not work out well. Torsion springs on the weights to allow them to hit a little harder, to hold things in place a little longer. Again, not a great design. The soft tooth quiet gears, we tried that, trying to reduce the amount of noise that these make. The soft tooth gears, unfortunately, they've got too much deflection in the teeth of the gears, and we would actually slip timing. We had some internal crashes and a lot of broken pieces. Magnetic weight swing controls. This is something that Roy Thornton was experimenting with. He was using electromagnets. He called them planet traps because of the planetary gear system, and he thought he was trapping energy and then releasing it when he needed to. They just did not work out well. I think the mechanical systems that we're using right now, especially with the ramps on the ends of the weights, is working out much better. We did try a latching lever weight swing control where the weights would latch into position, be held in place until they came around to a certain position. Then the latches would release. Worked great for a few minutes, and then the latches would start to malfunction and just bad things would happen. A lot of broken pieces again. And we've had a lot of really small component changes that, you know, that most of them were running changes that we don't even consider. You know, looking back at the notes, it's like, oh gosh, I forgot that we even tried that. They were almost inconsequential. The general specifications right now, we're using a 14-inch diameter wheel. The masses are 2 kilograms each. We're using a Chinese built 350 watt DC motor. It's designed to run 24 volts. It will run 12 volts just as well. It's basically an electric bicycle motor, so it's designed for long-term operation and some pretty hard use. We're using a pulse width modulated motor speed controller. It's a cheap unit. They're simply inexpensive, off-the-shelf components. We're using number 40 roller chain and sprockets for the drive. And right now we are using about 60 watts of power consumption. Now, we have not I have not personally put my lab scope on and verified that root mean square would actually show that 60 watts is our maximum, but averaged out with a meter, 60 watts is where we're running. So that's really not all that bad. As a quick recap, thrust is generated through a combination of impact, mass displacement, centripetal force, and the 4D gyroscopic flywheel. Where we're going from here, the testing, research, and development is continuing. We're continuing to improve the designs. We are making all of the technical details 100% open source, public information. It's available on my website. There'll be a link to the website shown in a few minutes, and I can always put one up in the chat. And with enough design improvement, I think that we really are going to have a unit that will actually leave the ground. And that will be a truly exciting moment when we actually can video a unit pulling itself up off the ground. A few last minute additional things that weren't originally in this. I wanted to mention that there's a swing test video online now. A lot of people have asked, excuse me, have asked me to put the unit on some sort of hangers so that they can see it move without any kind of a friction against the ground. I don't agree that this is a perfectly good way to do it. It passes the test. The video is online. Because it's a pulsed system and because of the length of the hangers, we had to slow it down. And so, yes, there is some swing back, but we'll hold in the positive direction 2 to 3 times longer than it will swing back for. It simply works. I mean, that's all there is to it. Road test data, we're road testing right now, the latest design. It's in the vehicle right now at this very moment. I've got to do some more adjustments to it before our next run. We generally put about 20 miles per test sequence on the units. 10 miles without it running, 10 miles with it running, so that we're running up and down the same test track over and over and over again under the exact same conditions. Engine load is what we're monitoring because that is the easiest and simplest indication of whether or not we've got good performance coming from the PI system. I think we need to change that configuration to 4 rotating wheels. I think that that's going to smooth the design, and of course it's going to increase the power by at least 2. I would like to change the speed differential control to an electronic sensor. I'm looking at optical sensors at this point. They'd be quick, they'd be easy, they'd be very easy to set up, and they're quite reliable. We need to smooth the pulsing. That's pretty much goes without saying. But if we change the configuration to 4 wheels and use the optical sensors, I think that's going to go a long way towards smoothing the pulse operation. The upcoming PIETECH. I mentioned this when we talked a while back. Mark had me on. We talked about it a little bit. PIETECH is a system that's an up and coming system. I don't have full information on that I can release just yet. It will be released eventually, but right now it's not entirely my design, and until I have permission, I'm simply not going to step on anyone's toes and cause anybody any undue pain, suffering, or anything else. That one, however, I can tell you that uses a new set of power storage designs. There will be a complete set of power storage units built into it, and that should also help make the system much, much smoother. I do have a quick compilation of just all the different units that I've ever had in the shop that we've built that would actually self-propel. Again, there's background noise, but I didn't add music to this one, so don't shoot me on that one. the noise is going to be from the units themselves running. So this gives you a really good idea of why we're talking about wanting to put this either in a box with something to dampen the noise or quieter components. We've talked about that on the videos. If you go to the YouTube channel, that's what we've talked about there. So here we go, self-propulsion clips. Going forward. As you see, I've had to hold on to it so it doesn't stick out on me. I've just got this sitting on some pieces of pipe because it's not really ready to be put with the other unit yet. So now, even without the speed control, speed differential control operating, yes, DC. Now with it, I do. I call that a success. I know I had some people that insisted that that didn't show anything, but the carriage underneath it actually rolls easier than it does. It's not pushing on it. It's not pulling on it. It shows definite self-propulsion. I want to thank everybody for watching, for staying with me this long. I tend to be a little on the boring side, and I didn't have a terrific presentation, but I threw this together because I wanted to let everybody see what we've got going on. My website, www.stclairtech.tech. There's links there to all of the blog information. That's all the builder information, starting from basically right at the beginning of the project all the way through to where we're at right now. It's also got links to the videos. It's got a link to my email, stclairtech@stclairtech.tech. The videos can be seen at YouTube at St. Clair Tech RD. Tokyo Muramatsu, he's done some amazing things over the years, and then he's been working on a Pi system. He's been working on the Pi 3 series, and he's done some absolutely amazing things with just 1 or 2 weights on there. I encourage anybody to go and take a look at it. His YouTube channel, DFTDMT. Just type that into the search, and it'll take you right to his YouTube channel. And of course, Tom over at Integrity Research, I can't thank him enough for some of the help that he's given me and some of the information. He's got a huge assortment of information, books, videos, and such over at integrityresearchinstitute.org. So that's pretty much all I've got at this point. And I really appreciate everybody staying with me and listening. And let's see if I can figure out how to unshare my screen. We'll be in pretty good shape.
Oh, Brian, actually, I can do that for you. So let me do that. I'm going to do stop sharing.
Beautiful.
And actually, before we do anything else, I'm going to put this on gallery mode. Everyone, please give Bryan St. Clair an enormous applause. Sir, thank you for presenting that. I thought that was a great presentation. And I mean, you covered a ton of different stuff.